So as we continue our discussion of Lewis structures, we got to talk about bond order and how that relates to bond strength. What the heck is bond order and bond strength? Well, we've seen a plot like this before that says you bring two atoms close together and there's an energy minimum, this little guy down here, an energy minimum that says they're making a bond, those two elements are sharing electrons, bring them closer together and they repel each other, the two nuclei repel each other. This is the bond length for whatever atoms are coming together. So we saw it as two F's coming together, but it could be two H's coming together. It could be an O and an H, any kind of thing coming together. There's an energy minimum on this plot. That tells me the bond length. The distance between the two nuclei is defined as the bond length. The bond length relates to atomic radius. What? Yep, remember atomic radius from the last chapter. We need to remember radius trends. So on our periodic table, we said atomic radius gets bigger as you go left and bigger as you go down. And we got to remember why, but we'd said those were the trends. So we hopefully remember that hydrogen is a pretty small radius atom because it's only got one shell of electrons. So when a hydrogen makes a bond to another hydrogen, those two nuclei are quite close together, and their bond length is 74 picometers. But when hydrogen makes a bond to iodine, iodine is way down there on the periodic table, so iodine's radius is larger, which is naturally going to make the two nuclei, hydrogen and iodine's nuclei, further apart, so its bond length is longer. Longer bonds are generally weaker. Why is that the case? Well, in order for that bond to have strength, those electrons need to be strongly shared between the two atoms. And when that distance is long, they're not held as the electrons between those two nuclei are not held as tightly, not held as strongly, so that bond is easier to break. If we relate it way back to chapter 4, HI, we actually labeled as a strong acid. What does it mean to be strong? We labeled HI as a strong acid because it dissociates in solution. It's actually because that HI bond is very weak. This bond much weaker than that bond. When bonds are strong, acids are weak. When bonds are weak, acids are strong. Yeah, takes a minute to wrap your head around that. Here's a list of some typical bonds and their distance. Note, this is in picometers, and this is in something called angstroms. Angstroms and picometers are related. They're both units of length measure. So this would be 154 picometers, 133 picometers. It takes 100 picometers to equal 1 angstrom. I think I said that in the right order. So these distances, we're not going to do any math with the distances. You can look at things in angstroms or picometers, it doesn't matter. But these distances tell me or relate to me the strength of the bonds. This is a carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. The triple is the shortest, therefore the triple is the strongest. The single is the longest, therefore it's the weakest. Carbon-nitrogen single, double, triple, same exact trend. The triple is the shortest bond, therefore the triple is the strongest bond. The stronger the bond, the shorter the bond, or the shorter the bond, the stronger the bond. Triples are shorter than doubles, are shorter than singles, and it goes in that same order of strength. So, here's a carbon-oxygen bond. If I cleave that bond, I get these two things. When I cleave a bond like that, each atom gets one of the electrons that they used to be sharing. That's why we've got these little dots over to the side. If I break this bond, that one, I should tell you first before I click. How much energy does it take to break that one? It takes 350 kilojoules per mole to break this CO single bond. What if I try to break this CO double bond? Is it going to take more energy or less energy? More. In fact, it takes 800 kilojoules per mole to break that CO double bond. And what about the CO triple bond? It's going to take even more energy than the double bond took. It takes 1086 kilojoules per mole. These values in red and purple and green are called bond enthalpies. Remember the word enthalpy from chapter 6? Bond enthalpy, the energy required to break bonds. So let's take you back to our enthalpy discussion. Back in the day when we started talking about enthalpy, we said delta H of a reaction could be calculated by products minus reactants. Well, it's kind of the same here, but a little bit different. Because we're considering bond enthalpies, we consider it total energy input minus total energy output. Input minus output. Okay, in the case of bond enthalpies, it's how many bonds or the energy required to break bonds minus the energy released when bonds are made. So broken minus made. Products minus reactants, if you're given whole molecule enthalpy values, it's usually for ionic compounds actually. Broken minus made if you're talking about bond enthalpies. But we draw enthalpy plots the exact same as we did previously. You go from reactants up to broken down atoms. That's an endothermic transition. Then you go from atoms to products. That's an exothermic transition. And because the chart is this shape, this specific reaction is endothermic overall because your products have less enthalpy than your reactants. So if we look at a quick example, looking at this reaction up here, H2 plus F2 yields 2HF. Bond enthalpy values are given here. Broken minus made, we need to break down H2, that's this. We need to break down F2, that's this. And we will make 2 HF bonds in the process. So if we draw a little plot, breaking down H2 and F2, endothermic gets broken down into gaseous atoms up here, and then exothermic releases energy as you form 2 molecules of HF. We really could and should verify what types of bonds we are breaking. H2, the Lewis structure of H2 is HH, like that. The Lewis structure of F2 is this, with all these little lone pair electrons out here, right? Yep, and we're going to make HF, which is a single bonded thing, 2 molecules of that. So it's this reaction is overall endo or exo, exothermic overall. And the way we would calculate it is delta H is 436.4 plus 156.9 minus 2 times 568.2. This plus this minus 2 times 568.2 yields this exothermic enthalpy value. So when you check out enthalpy values in a table, like table 9.4, you will often see multiple enthalpy values. It's not a great example for me to talk about it for this, but I'm going to take a minute anyway. You will see a carbon-carbon enthalpy value. And you see different delta H's depending on the type of bond it is. So how does this enthalpy stuff relate to Lewis structures? You will often have to draw the Lewis structure of a molecule to know if you need the enthalpy value of a double bond or if you need the enthalpy value of a triple bond. You don't want to plug in this value into your broken minus made if you are actually dealing with breaking a triple bond. So you got to be able to draw the Lewis structure to know what types of bonds you have, to know how those things break down energetically. Okay. Remember, valency determines the number of bonds that the atom forms. What? Carbon is in group 4, and because he's in group 4, that means he has 4 valence electrons, and everybody on that period 2 wants to have 8 electrons and be like neon. We're really talking about the non-metals over here, but I just highlighted all of period 2. We're talking about non-metals, want to be like neon. That means carbon needs 4 electrons to have 8 in its valence shell. It means it likes to make 4 bonds. Neon is in group, nitrogen is in group 5, which means he's 3 electrons away from having 8. He likes to make 3 bonds. Oxygen's in group 6. That means he's 2 electrons away from being like neon. He likes to make 2 bonds. All of the halogens are 1 electron away from their outer shell being full, so they like to make 1 bond. Hydrogen has 1 valence electron, but it only needs 2 in its valence shell, so hydrogen likes to make 1 bond. We use these hints, this information, to help us build Lewis structures. So let's practice a couple of Lewis structures. The first thing you do when you draw a Lewis structure is add up the total number of valence electrons. Oxygen has 6, plus hydrogen has 1, plus this little negative charge tells me I have 1 extra. So there are 8 valence electrons, 8 electrons to work with in OH minus. I'm going to draw a single bond between O and H because I always start with a single and then I make more bonds if I need to. So a single bond between O and H, H can only make 1 bond anyway. And then I fill up the octets of everybody. Oxygen's octet is now full, and hydrogen, his octet, except it's not really an octet because he only likes 2 electrons, his octet is also full. I go back and count. 2, 4, 6, 8 electrons have been used. 8 electrons is what I was allowed to work with. This is good, except I need to show that this molecule is negatively charged overall. That's where my extra electron comes in. So we start by adding up valence electrons in the next one. I get hydrogen plus carbon is in group 4 plus oxygen is in group 6. That gives me a total of 12 electrons to work with in this molecule. Well, hydrogen likes to make 1 bond, oxygen likes to make 2 bonds, and carbon likes to make 4 bonds. So that really kind of helps me start to see that carbon must be the central atom, and oxygen and hydrogen must be connected to the carbon because that makes carbon closer to having the number of bonds it wants to make. Carbon likes to make 4 bonds. So if I draw this thing, which is sometimes called the skeletal structure, it's putting together things with single bonds, then I can go back and fill in lone pairs to make everybody have an octet. So that means 6 electrons around oxygen and 2 electrons around carbon, and hydrogen has enough around each of them. Go back and count to see how many I've used. 2, 4, 6, 8, 10, 12, 14. I only had 12 to work with, and I've used 14 in my Lewis structure here. So the way I do that is -2, -4, turn this bond into a double bond. So that's sort of formal Lewis structure rules. I have now used 2, 4, 6, 8, 10, 12, and I had 12. This is a Lewis structure of H2CO. It also matches because carbon likes to make 4 bonds, and carbon is making 4 bonds, which gives it 2, 4, 6, 8 in an octet. Oxygen likes to make 2 bonds, so oxygen is making 2 bonds. It gives him 2, 4, 6, 8. Hydrogen likes to make 1 bond, done. Hydrogen likes to make 1 bond, done. This is a great Lewis structure because everybody is making the number of bonds they want to make. Is it illegal to have them make a different number of bonds that they want to make? No, unfortunately over here is an example of oxygen likes to make 2 bonds, but there was no 2 things to bond with over here. So that's just not possible in hydroxide. Everybody's happy over here. It's good news. Okay. 4 plus 4 plus 1 plus 1 gives me 10 electrons in C2H2. Carbon likes to make 4 bonds. So if carbon is connected to carbon, the way that makes sense to me, carbon likes to make a lot of bonds, so let's put some hydrogens on each of those carbons as well. And then the official Lewis structure rules say fill up the octets of everybody. If we did that, we would see that we used too many because the problem is carbon likes to make 4 bonds. And in this molecule, each of the carbons are only making 2. So if I do a little this number, that makes each carbon now make 4 bonds the way we want it to. It makes hydrogen make 1 bond the way we want it to. 2, 4, 6, 8, 10. That's the perfect Lewis structure of C2H2. It's excellent. Okay. Phosphorus has 5. Chlorine has 7. That gives me 26. If I just did my math correctly, I believe I did. So if I want to draw the Lewis structure of PCl3, well, I can start with phosphorus with Cl's connected. So you want the thing that's capable of making the most bonds as your central atom, most of the time at least, because that thing can hook everybody else to him to make this whole molecule come together. So chlorine likes to make 1 bond. Phosphorus actually likes to make 3. He's nitrogen's downstairs neighbor. So this seems legit as far as number of bonds are concerned. So then we fill up everybody's octet. Chlorine needs 6 electrons to fulfill its octet, so this is making 1 bond. So I put 6 electrons around each of the chlorines. Phosphorus needs 2 electrons for him to have a full octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 26, whoop, whoop. This is PCl3. And lastly, if we draw the N2H2, that's 5 plus 5 plus 1 plus 1, that's 12 electrons to work with here. Nitrogen certainly likes to make more bonds than hydrogen, so let's bond nitrogen to nitrogen and a hydrogen on either side. Nitrogen really likes to make 3 bonds, so if we put in an extra bond between the 2 nitrogens, that seems reasonable. That gives nitrogen 3 bonds, nitrogen 3 bonds, hydrogen 1 bond, hydrogen 1 bond. Okay. So if I counted 2, 4, 6, 8, I've not used enough electrons. But my octets aren't full. Nitrogen only has 6 electrons around it. If you counted the bonds, it's 2, 4, 6 electrons around the nitrogen. 8. 2, 4, 6, 8. Now, each of the nitrogens have a full octet. 2, 4, 6, 8. 2, 4, 6, 8. And overall, we've used 2, 4, 6, 8, 10, 12 electrons. Lewis structures are something I can talk to you about until I am blue in the face, but it only starts making sense as you practice and practice and practice some more. I'm sorry, but it's just the truth. Good luck with them.